Thank you for joining us today. I wanted to present on a recent laboratory testing project we did at the Western Cooling Efficiency Center, indirect evaporative cooling for residential applications. And I'm Theresa Pistochini. I'm the engineering manager at the cooling center. And just want to recognize that this work was mostly conducted by staff on our team, Curtis, Derek, and Robbie. So just some background on how residential air conditioning typically works. You can see my pointer, Allie?
Yep, we can see where you're moving your mouse.
Okay, so basically this is just a cross-section of a single-family home. I have to recognize Paul Fortunato for these graphics, but so up here you have generally an air handler in your attic. It might also be like in a closet. You bring in return air from your space. You have a fan, generally in California, a gas furnace, and then a refrigerant coil that provides cooling. And then you have supply ducting that goes to various rooms. In newer construction, you may also have an outdoor air intake to provide ventilation to the home. And then you have refrigerant lines running outside connected to a condensing unit, which rejects the heat from the air conditioning portion outside. And so this is how, the vast majority of single family home construction is done. And I just wanted to talk today about an alternative that incorporates indirect evaporative cooling for the cooling part of this equation, which is this refrigerant coil and condensing unit. So I just wanted to give some background on what indirect evaporative cooling is. So basically, evaporative cooling uses the latent heat in evaporating water to cool air. So when you evaporate water, you take, you drop the temperature of the surrounding air as you evaporate that water. The simplest form of evaporative cooling is direct evaporative cooling, where basically you run air across some kind of wet media and you drop the temperature of that air as it goes through the media. The problem there is you add humidity to your air, which is often undesirable. So there's a process called an indirect evaporative cooling where you have some other sort of heat exchanger. So in this case, you take hot, dry outdoor air, you send it through the dry channel, part of it turns around and it's then evaporated. Water evaporates in the wet channel and cools that air and picks up the heat across this, this plate. So indirect evaporative cooling, any kind of evaporative cooling process like this doesn't have a compressor or refrigerant in the traditional sense. In the product that I'm going to talk about that we tested in our lab, it's a combination indirect and direct evaporative cooler. So after the air comes from outdoors and is cooled, there's a final stage where it also picks up a little humidity and cools a little bit further. And I thought if it works, I wanted to show just like a minute of this video that Paul made for another purpose. But this actually shows how the indirect evaporative heat exchange process works. So does it work, Allie, the video and the sound? Or
I haven't heard the sound yet, but
I think if let me see if I unplug my headphones, I think it'll go through my mic.
And adds no humidity.
Yep.
Does this by using the indirect evaporative cooling process. Let's explain that further. The heat exchanger in the climate wizard is made up of a series of alternating wet channels and dry channels, which are designed to transfer heat between them. Hot outdoor air enters the dry channels of the heat exchanger through a high efficiency fan. After air passes through the dry channels, a portion of the air is supplied to the building and the rest returns through the wet channels. This is where the evaporative cooling process takes place. The evaporative process cools the wet channel walls. As these walls cool, they absorb heat from the dry channel air, cooling the air delivered to the building. The portion of air supplied to the building is controlled by a damper.
Anyway, let me just get my headphones back in. Okay, so I just wanted to show that because I think that's just a great visualization of it. I just wanted to show what this looks like on a psychometric chart. Evaporative cooling processes essentially only work when you have the potential to evaporate water, so you have to have sufficiently dry air. Let me just put some of this up here. So basically, in indirect evaporative cooling, you are moving straight along the dew point line as you sensibly cool without adding any moisture. And then in direct evaporative cooling, you directly add water and you go along a constant wet bulb line. So if you're out here at 110 degrees on a dry summer day in Davis, for example, the theoretical minimum supply air temperature out in an evaporative cooler in a perfectly optimized system essentially would be like 45 degrees Fahrenheit. It's not really practical from like a surface area and fan power perspective to achieve something like that. But for example, something more like 55 degrees would be possible in a 110 degree outdoor air condition. And so then the question is, where is evaporative cooling a potentially useful solution? That's going to occur when you have big differences in the dew point temperature versus your maximum daily dry bulb temperature. And so you can see here in the Western United States, there's just a lot of potential here because we have, and to save energy, right? And use evaporative cooling because we have days where, dry bulb temperatures are easily over 100, but the dew point is closer to 50. Here's an example day in Davis. You can see that the dew point temperature is really stable throughout the day. So in the realm of 50 degrees, and you can see the outdoor air dry bulb temperature increases to, over 100. So shifting gears, I want to talk about a specific new product that we tested called the Climate Wizard 3 that Sealy is introducing to the California market. So basically, it is a combination indirect and direct evaporative cooler. This is sort of a cutaway of what the system architecture looks like. And this is also showing how we instrumented this device in our lab. So basically the outside air comes in here. We measure its temperature and its dew point. It goes through the indirect evaporative cooler. Some of that air is used for the exhaust process and it gets exhausted outside. And then the rest of it goes to the direct evaporative cooler and is supplied to the building. So we measure also the supply air temperature and humidity are important measurements, and then also the supply airflow, which is critical to determining the cooling capacity. We also measure the static pressure across the duct. That tells us we have to simulate sort of duct system resistance in the lab. We also measure the power of the fans, the power of the pump, and the exhaust conditions as well. In this particular piece of equipment, you can control the indirect and direct evaporative cooling portions separately. So in theory, you may want to, depending on the trade-off between a little extra cooling and a little extra humidity, might want to adjust that. And then the fan speed is also completely adjustable, has 10 discrete speeds. So then I had to hack up this drawing here because I didn't have time to ask Paul to draw me a new one. But so then I just wanted to say, okay, so how would we switch out a compressor-based air conditioner for a Climate Wizard? And I show it here sitting on the roof. It wouldn't necessarily have to be on the roof, but it made my drawing easier. So basically you have this indirect evaporative cooler using outside air, and then it's supplying a portion of that air to the building. Well, in this particular case, this system is designed not to use any return air. So if you wanted it, the problem is you still need heating. So you would still need your air handler and your gas furnace. And then you could switch out your compressor-based air conditioning for the Climate Wizard or some other similar type of system. The advantage to this is now you don't have any refrigerant in your home, but on the downside, you're still burning natural gas, right? So these are trade-offs. But this is one possible retrofit strategy for this technology. What you have to think about when you do this is that the supply airflow for the Climate Wizard is greater than you would expect for a typical air handler. So we're going to have greater resistance in this duct system, and you'd somehow would need a damper to sort of swap back and forth between these two systems. There's definitely some movement in the direction of combining indirect evaporative cooling with heat pumps, and with the eventual goal that you could just replace your entire air handler and gas heating setup with a product like this. So we lab tested, this is the Climate Wizard 3 here on this test stand that we built, and some of the engineers that worked on the project. And we've got here just showing you there's these on all three, I believe on three sides, there's the evaporative cooling modules. And so you can see here this is the indirect portion on the front, and this is the direct evaporative portion on the back. We have environmental chambers at the cooling center that we can use to create outdoor air conditions of basically whatever we want. And so this is, it's a little crowded in there, but you can see the Climate Wizard 3 installed in the lab. The ducts down here are the supply airflow. Out the top is coming the exhaust, and then this chamber is conditioned to the outdoor air conditioning, comes in on all of these sides. And then you can see all of our instrumentation. This is our data acquisition box here on this stand. This project was funded by San Diego Gas and Electric, so they're particularly interested in San Diego climate zones. You can see here 2 climate zones in San Diego territory. Climate zone 7 is coastal, very mild. This is one data point for every hour of a typical weather year. And so there's a lot of winter data in here as well when you would not be cooling. And then climate zone 10 is also in San Diego territory, but it is much warmer, it's more inland. And so we picked some test points here between 85 and 115 at increasing humidity, recognizing that this product will also have applications outside of San Diego. And so we want to pick up some warmer weather conditions, and just recognizing that below 85 Fahrenheit, that a lot of people won't really even operate a residential cooling system. And so we tested the Climate Wizard at these 9 test points at 3 different fan speeds. And that will allow for the development of performance maps for energy modeling. I won't go into this in too much detail, but we put some thought into deciding what external static pressure to test at. As I mentioned, you'd have to connect this system to a existing duct system. And so we basically had a high static pressure condition. And this is going to directly affect the fan power, so that's why this is important. We had a high static pressure condition, which we calculate is for replacing a 4-ton air conditioner in a home, and the lower static pressure would be if you're replacing a 5-ton air conditioner, because those systems have larger ductwork. So our performance metrics included measuring the total sensible capacity. That's the change in air temperature times the flow rate, basically. We also measured the sensible room capacity. So if you just measure the change in air temperature, you're dropping the air outside from, say, like 115 to 60. Well, one would argue that you don't need all that outside air. So like a typical compressor-based air conditioner would only be dropping the air inside from 80 to 60, for example. And so a room capacity only takes credit for the cooling below the indoor set point, which we assume to be 80 degrees. So we also calculate the sensible room capacity, which basically, as I said, just discounts cooling of the air, which does not include, I'm using the words discount here as meaning it does not include the cooling of that from the outdoor to indoor condition. And so in this case, you don't get any credit for cooling all of that ventilation air. And then we also calculate the sensible room EER, which is an efficiency metric, basically the sensible room capacity divided by the fan and pump power. Okay, so here's some results. So you can see here that the sensible room capacity of the system is on the order of, depending on the condition, you can operate the speed such that you can obtain anywhere from 30,000 to 60,000 BTUs per hour. That's nominally 3 to 5 tons. That is typical of the range of capacity of a residential compressor-based air conditioner. These different shapes represent increasing dew point. So for lower dew points, you can achieve more capacity. Probably the triangles are more representative of what you would expect in Northern California on average. And you can see as we increase speed, we are generally able to get a little more capacity as well. This shows us the EER of that process, the efficiency of that process. A typical older compressor-based air conditioner would probably have an EER around 10, and maybe a variable speed, high efficiency, brand new system, you might be able to get like 18 at certain conditions. So you can see here that the efficiencies of an evaporative cooling process are much higher by factor of 5 in many cases. Efficiency goes down with increasing fan speed, and it also goes down with increasing air temperature and humidity. I also have the low static pressure results, but I'm just going to skip over those. They're similar in trend. Anyway, so conclusions. Cooling efficiency was excellent at many climate conditions. Most tests were between 20 EER as high as 105. Capacity does struggle under hot, humid conditions, which you would expect. And this technology is designed for dry climates. Bringing in this outdoor air into the space, you have to essentially figure out, how to do that. You might need some pressure relief for your building. And then in a case where you're using all this outdoor air to provide cooling, it's relevant to point out that in a situation where you have good quality outdoor air, most of the year, absent, terrible wildfires or something like that, overall with filtering, you would expect that using a product like this for air conditioning would improve your overall indoor air quality by removing indoor contaminants.
I'm curious about kind of the cost of this from a retrofits perspective versus the current kind of options on the market.
So this product isn't actually commercially available yet. This was like the first one that we tested in our lab, and now they're doing several houses as demo sites in San Diego Gas and Electric territory. So they'll be gathering cost data on that. As far as the cost would be high because of a lack of volume, right? Because this is not a typical way of doing air conditioning in California. But really, as far as the cost associated with the design and the components at scale, you would expect that the cost would be comparable or less than a refrigerant-based system.
I've titled it District Energy and the Pathway to Carbon Neutrality on Campus. You probably all know that the campus is has this goal of carbon neutrality for 2025. And district energy is a big part of that. And I want to talk about how that plays into this carbon neutrality goal. So if you haven't noticed before, just to mention, this picture here on the title slide is picture not just the soccer field and a water tower, but on the left there where you see the steam rising into the air, that's our central heating and cooling plant. So that's kind of the heart of the district energy system. That's just actually warm exhaust coming out of our boiler and condensing in the cooler air outside. This is on a cool evening, I think. But if you haven't had a tour there, I do want to mention I just gave a tour to a class. Some of you, I think, are in that class earlier this week, and we're going to have a video made of that tour as well. So we might be able to share video tours of the plant in the future if you want to see that. So you can reach out to me if you want to see that as well. But I'm not going to talk a lot about the plan. I'm talking more about the overall campus goals and district energy. So let me move on to this next slide here. Just in case you don't know me, a little bit of background. I'm the energy manager in facilities. I run a team called Energy and Engineering in facilities, and we are an engineering support team in facilities supporting the operations of the campus. And so we do a lot of work related to energy on campus. We have a team that's just called Energy Engineering, and they focus on energy savings on the campus, a lot of optimization of the building systems, and especially the heating, ventilation, air conditioning, like Theresa talked about, but on a larger scale. And we have a team that manages the controls systems in those buildings, so doing advanced control sequences and things like that. But we also have some teams that do outreach and engagement on the campus. So that if you haven't seen our campus energy education dashboard or some of the other apps we have out there, you can go on our website at facilities.ucdavis.edu and take a look. I'm a graduate from UC Davis in mechanical engineering. I worked in the consulting industry before I came to campus a while ago. So I've been here a while, and I've been working on this concept of district energy since I got here, and especially trying to get to a more sustainable solution, which is where we're headed now, which is exciting. So real quick, I'm going to just cover some of the goals for the presentation today. I'm going to give you just one slide on the campus carbon neutrality goals, a brief overview of our district energy, and I'm really going to focus on the district heating system conversion project that's going on right now and how we got to where we are. So if any of you get back on campus anytime in the future, hopefully, if not, over the summer, maybe in the fall, we'll be able to be back on campus some, but there's going to be a lot of trenching going on, and this project's going to be in full swing, actually starting here in June. They'll be digging up some of the streets on campus. So if you're wondering why, hopefully I'll give you some of the background to that project. And it's hopefully going to be the case from now through 2025, maybe a little bit longer as we do the entire campus. So the overview of our carbon neutrality goals, I'm not going to talk a lot about that, but the basic goal is scope 1 and 2 emissions to zero by net zero, but by 2025. So the campuses, the great thing about this is all the campuses have made a plan. This is a shot from the FOVEA CAP. It's a carbon planning tool that we're using for the UC system. And this just shows the UC Davis recommended actions that we can take to get from where we were. This shows it in 2017 snapshot there with the gray showing history and our emissions on the top chart in the black trend. And then it shows if we want to get down to 2025 with the dashed dark line going forward from there, it's a pretty steep curve. If we didn't do anything at all, we'd be going up along the top trend there with all the colorful wedges beneath it. That's if we just continued to grow and didn't do anything about reducing our carbon emissions. But there's a lot of things that we are doing and can do. And so this shows each a slice or a wedge for each action that we can take to get down to carbon neutrality. And this includes our med center in Sacramento as well, which has a big chunk of our carbon emissions because of its cogen unit. But the one thing I wanted to highlight here is there's a main campus hot water conversion. It's a red slice, the bright red slice in this wedge chart, which is a big part of the main campus, at least in terms of what we can do for carbon neutrality. And the other thing to notice here is just on the bottom chart, the two charts below are showing capital expenditures over time, cumulative, and then annual operating expenditures. And with some initial investment over these years, the exciting thing is the operating expenditures actually go down. So carbon neutrality does actually come with savings and ends up being a more sustainable operation, which is why it's one of the reasons it's our goal. UC Davis has 2 district energy systems. Right now, they're completely independent, and I've shown them separately here, just a snapshot from a facilities map tool we use. And this just shows the main campus here with kind of the web of district energy piping in different colors. On the left side of the screen is the district heating system, and on the right is the district cooling system. So there's 27 miles of pipe for each of them approximately, plus or minus a mile or so. But that's counting all the pipe supply and return. It's a lot of pipe though. It's all underground, and it's been installed over the last 50, 60, 70 years. And so it's in various conditions. The steam system does go out to the campus buildings from the central plant at about 350 degrees. That's at 135 PSI, and comes back as condensate, we call it. It's just steam that's condensed back into hot water after it's done its heating, and it gets pumped back to the central plant so we can reheat it and reuse it again. And about 90% or more of that steam that goes out comes back to be reused. And then the chill water has 40-degree cold water going out in the cooling system. So we cool it down at we have 2 cooling plants, and we run chillers in those plants that cool the water down to 40 degrees, goes out in these pipes. It's a closed system as well, so it goes out and then comes back as warmer water. It's picked up heat from the buildings. But these are 2 separate systems right now. I do want to note that one of the opportunities with district energy is to tie these 2 things together, because the district cooling system, one way to look at it, is a heat collection system. It's actually just collecting heat from the buildings when it cools them off. Right now, we're bringing that heat back to our central plant, and we're throwing it away in our cooling towers, meaning we're just rejecting it back into the atmosphere and it's doing its job. It's cooling the buildings, but we're not reusing that heat. So one thing we want to do is to take advantage of all that heat that we're collecting from the buildings. We can't do that with a steam system because of the temperatures that it's at. As you see, it's a high temperature system. So talking more about the steam system, like I said, it's a lot of pipe. It's old. It serves a lot of space on campus. Pretty much the entire campus from this aerial view in the background is served by this steam system. About 8 million square feet of our total campus, and then 32% of our campus carbon footprint. So as we talk about carbon neutrality for the main campus, this is a huge piece of it. We have to deal with this steam system. The reason is it's to make this steam at these temperatures that you need to make it at to make this system work, it has to burn natural gas. And so that ties you to a large carbon footprint. It's also a very old system. You can see the purple pipe in this diagram is old. It's now over 50 years old, and there's a lot of sections that need to be replaced. These numbers on this map here are showing potential expenditures to replace or renovate or repair different areas of the steam system around campus. And this was kind of the opportunity for us a few years ago to say, do we really want to spend more money on this system, or is this an opportunity for us to do something else? The steam system, just by its nature, because of the temperatures that it runs at, is inherently very inefficient in distributing energy to the campus. Our steam plant itself is very efficient, about as efficient as you could possibly make a steam plant. It gets up above 90% efficiency with the condensing economizer that we use, but the distribution of that steam at 350 degrees is bound to lose a lot of energy over that 27 miles of pipe. And so we've estimated over 30% energy loss. At times it gets up to 50%. For example, in the summer, we still are using heating in buildings based on the nature of these systems. They still need to have some zones with heating. There's also steam usage in buildings for various processes. And so the entire steam system, this 27 miles of pipe, has to stay energized with 350 degree steam. And when very few buildings are using it and the usage is low, you can imagine that the losses in those pipes are very high, that it's all condensing back into hot water and coming back to the plant without ever having done any heating out there. So could be very high losses. And when we talk about how much we spend on utilities for the campus, we're over 20 million a year, and a large part of that is on gas, natural gas, and so the losses are directly impacting our utilities budget as well. So we are faced with the decision: do we want to invest more in this steam system? And the big opportunity that we really wanted to leverage here, this is a chart that AEI put together from some of our data, and just focusing on these colored areas here, you can see on the top of this x-axis here is showing the cooling needs for the campus. And you can see in the summer months of June, July, August, our cooling, shown it here in millions of MBTUs, are pretty high. And then they drop off very low in the winter. In the same way, our negative axis here is showing heating needs in the winter are pretty high. They're much lower in the summer. And then it gets high again as the winter comes on. But the opportunity here is that there's some simultaneous heating going on. Now this is looking at monthly heating and cooling needs, but even if you look at the daily, there's daily heating and cooling every day of the year. And the opportunity is what's shown in these lighter shades. So this is saying that if you, as I said, the cooling system is a heat collection system. So if you use all this cooling and you're taking that heat out of the buildings with that cooling profile, and throwing that heat away, you can take some of that cooling and put it into the heating system if you had a heating system that could use it. So what this is saying is there's a potential here for heat recovery. Take some of the heat collected in the cooling system and then use it to do your heating needs. If you had a system that could use the low grade heat that you're collecting and you have a way to store it, so you can do daily storage. So if you're collecting heat during the day and the afternoon when you're cooling, you can then use that heat when you need it at night and in the mornings when you're doing heating. Steam is not able to do either of those things. It can't use the low grade heat and it can't do storage. So that made us really start looking at other options. And so we had some goals going into this analysis as we were doing master planning with AEI on our district heating system. We wanted to have a safe and reliable system. Obviously, we want to do some modernization, do renewal in the process, not just patch up an old system. And we really wanted to take advantage of these district system opportunities like I talk about. When you're bringing everything back to a central point, you can do more with sharing, which we aren't doing currently. And then we wanted to overall be able to use the university's money in the best possible way. That, hey, we're going to be here a long time, but we want to have the lowest life cycle cost, and we want to support the goals of the university. So what we did with AEI was it's a long-term 60-year life cycle cost analysis, and these numbers are just really to have a relative comparison, looking at different options for what we could do with this heating system. The 60-year life cycle is very long, and but the reason we did it that long is so that it would capture the full life cycle of all the components in the system and the replacement value, so that it would be a fair comparison. And even though we don't really know what's going to happen 60 years from now, it at least allows us to have a good side-by-side comparison of these different options. So what this is showing is the different types of expenses that each system would have. And starting on the left here, this first option is just to keep the existing steam system, but make fixes where we need to and keep it working. So that's going to have a significant investment in capital. The gray on the bottom is the capital expense. Over that lifetime, we're going to basically have to replace the entire steam system with new steam system as the pipes need replacement. Then there's a maintenance, just ongoing maintenance of the system, which is the orange and white here. And then the solid orange is showing the natural gas operating expenses just to keep this steam system running. There's also electricity involved, not as much because it's mainly a gas-fired system. And then there's some significant carbon costs. This is all with, we did a lot of analysis on sensitivity of potential carbon costs. And so we used numbers here, and we've looked at the impact of changing those numbers within the potential range of what's out there, and really didn't change this analysis in the end at all. But what we compared that business as usual case on the left to is, let's just look at if we convert to hot water, just put in hot water pipe. It's going to cost a lot up front. In the long term, though, if we just put in new hot water pipe, it's going to cost less than putting in all new steam systems. So over the life of the system, it's actually a little cheaper capital wise. We're going to have to find a way to pay for it up front, though. But there's a lot less maintenance on a hot water system. There's a lot of systems out there, especially in Europe, that have data that show that the operating or the maintenance expenses on a hot water system are much lower than steam. We're still going to have to make hot water with the boilers, and so that's still a big gas usage, and slightly less because we're going to have less losses and less carbon as well. The next option is to take advantage of that heat recovery, where let's try to use all that heat we're collecting in our chilled water system and change out some chillers or add some heat recovery chillers, some heat pumps essentially that can take the heat from our chilled water system and step it up to something we can use in our heating system instead of just throwing that heat away in a cooling tower. So this is talking about central cooling and heating. And this is where we would, or with heat recovery. So this is now going to use more electricity to run those heat pumps and a lot less gas, because we're not doing as much gas heating. We're still going to need gas in the winter when we don't have enough cooling to do all the heating with heat recovery. It's going to cost a little more up front and maybe similar maintenance because not much changes there. It's still a new hot water piping system, but now we're doing more of the heating with heat recovery and less with gas. So it gets us toward our carbon goals, a lot less carbon usage. What we ended up landing on was these two solutions. We basically are keeping the options open for both of them. I'll talk about those, but the last one here on the chart is showing the potential of, instead of having a central heating system with piping running to all the buildings on campus, what if we just had a distributed heating system still tied into, for example, the chilled water with heat pumps, but had distributed heat pumps throughout the campus, which is a great innovation, I think, but it ended up being too expensive on the capital and the maintenance side because you end up with then, if you're talking about multiple heat pumps or maybe a heat pump for every 5 buildings or something, you're going to end up with a couple hundred heat pumps with redundancy and everything out there on the campus that you have to maintain and install. So the numbers just got too big for a campus of our size, and it got too expensive. But looking at heat recovery on a central level, where we can still put in the hot water piping, distribute it, but bring that chilled water back to a central location, make heat with the heat recovery chillers or heat pumps, and then distribute it, is the best option. And what this does is throws in an airside heat recovery in the building, so getting some free heating essentially out of using less outside air. When we could use it to get free cooling in the buildings, we can instead basically get free heating by giving up some of that free cooling. And then that's the solution we're going with right now, with the option to eliminate gas completely. So the full electrification that still is feasible is in the winter months when we don't have the potential to do the heating with the heat recovery. We can run that chill water when we can't get the heat out of the buildings with the chill water. We can run that chill water into the ground and do geo exchange and pull it out at a warm enough temperature then to run our heat recovery chillers and make the heat out of that, or run it through air source heat pumps and pull heat out of the air. Either way, it's a little bit of an electrical load. Air source heat pumps would be more so, but the grounds geo exchange would be a more of a capital cost. So both of those are options for full electrification, and the path we're going down right now still has those in its sights, but it's just going to be a decision point when we get there. And you can see, it's going to be more expensive. Exactly how much more expensive we'll probably have to see when we're a little bit closer. So that some of the findings is just that doing this new distribution system with hot water is going to deal with all of our renewal and capacity needs. And we're going to end up with a much more innovative system that's going to leverage district energy and provide us with a pathway to full electrification and carbon neutrality. So this is the recommended option. I just kind of talked through that. We actually already have a hot water system operational in our Theresa residence halls that's right now running off of our condensing economizer off the boiler system. The waste heat from the boiler is generating hot water. So we have some experience with hot water and in a limited way on campus, but we also have a lot of other campuses that we've been working with and talking to for a number of years now that have either done this or are doing it and have been able to help us out in planning it as well. So here's another AEI diagram just to give you a feel for the campus systems. There's a lot here, but just to simplify it, on the right side are the building systems that are connected into this, I'm just going to call a loop here, and this is our district energy. But you notice that our heating system right now, this is the current system. Our heating system, we're burning natural gas in 4 boilers, and that is making steam, which goes out to heat all these buildings. It's completely independent of, even though it's in between here are other chiller plants, it's independent of them completely. And so heating systems are independent of cooling. The cooling, we have 2 chiller plants, one at the top here, which is our central heating and cooling plant. And then there's another chiller plant that's remote from that called our thermal energy storage chiller plant. They both have 4 chillers. The thermal energy storage has a tank, a large chilled water tank, 5 million gallons, that gives us a lot of flexibility about how we operate that. Those 2 are tied together into this chill water distribution system that does the cooling for the campus. So that's the current systems. And I'm going to show you what it looks like, our recommended solution now. Still has our chiller plant. We were looking at in the future converting our thermal energy storage chiller plant into heat recovery chillers. So as those chillers are at their end of life, we would be replacing them with, instead of just a chiller, a heat recovery chiller, which is a slightly different unit, which instead of just making water that can go to a cooling tower to get cooled off, it makes water that you can actually use at a temperature you can use it in a hot water system. So these are the future heat pumps. We're going to add a hot water thermal energy storage tank so that we can do that daily storage along with our chill water storage. And then it has the boilers still shown here for the life of the boilers, at least the 2 newer ones. We aren't going to just throw them away. We'll use them as backup heat. We'll use them in the winter with heat exchangers to heat hot water as long as we need to or as long as we can. But once those reach end of life, we need to have another solution. And so the ultimate goal would be to have this is showing here a geo exchange system where we can run that chilled water when we can't get heat out of the buildings in the winter, enough heat, we can run that chilled water into the ground, get it back up to 60 degrees, and that's enough then to run it through our heat recovery chillers and make hot water in the winter. It also shows potential air source heat pumps. You could do the same thing to heat that chilled water back up in the winter when we need some more heat to run our heat recovery chillers. So we'll either have one or the other or a combination of both for a fully electrified carbon neutral heating system. So in terms of implementation here, this is how we've broken up the campus. We're not Stanford. We can't pay for this whole thing in one fell swoop. So we already have Theresa on a hot water system. These are showing the 2 chill water plants, and the heating plant is right here. What we're doing is converting right now, we're converting this large area in red. Hutchison Quad is being converted to hot water initially, and so that's the one that's starting in June. That's going to finish up by the end of 2021, and hopefully that then we'll be able to shift in 2022 over to the next district, as well as some heat recovery down here at our plant, so that we can start heating these hot water districts off of our heat recovery system when those projects are done. And then the next step would be to shift to either the south area of campus or this health sciences, these districts here. But with the goal of having the whole thing done in the probably 2025 to 2027 timeframe, just due to the construction schedules, and of course having to find a way to fund it all. Right now we're funded to do this piece, and the conversation about funding for these other pieces kind of has to get in line with all the other funding on campus. So, but the campus is committed to the entire project, and that's what's exciting, is that we're moving forward with it. So here's the rough plan. It's changed a little bit in terms of what actually got bid out, and it is now under construction, but the basic idea is shown here. Our heating plant on the left, we're running new hot water pipe out to all these buildings to pick up all these buildings to be served off of hot water instead of steam. That'll allow us to turn off steam that currently serves this area of campus, which will get us some savings for not having losses in those pipes as well as in these buildings. But it's really just the first step of getting the hot water pipe in the ground in a place to start putting hot water, and then the next step will be to go to the heat recovery so we can have a better source for that hot water. And just to give you a feel for how we felt like it was a good investment for the campus, and this is part of the case we had to make to the campus to fund it. The cost of this project is about just under $60 million, which includes new heat exchangers to make this hot water initially off of the steam here at the plant, and then all the piping and all the building conversion work to make them run off of this hot water system. As a comparison, it was would have been about $49 million, just under 50, to repair all the steam that's out in this area shown in orange, which needed to happen in the next 5 or so years anyways. And then also we would have had to add another boiler for another $14 million in the central plant, just due to limitations. The 2 oldest boilers need to go away. And so the campus was faced with the decision, do we put another boiler in and keep going with steam? Well, instead we've been able to shift to hot water with the goal of reducing our steam load to the point where we won't need that other boiler, and then eventually won't need the boilers at all.
Josh, just real quick, I know we have a couple questions in the queue and just a few minutes left, so maybe just wrap it up with the last slide would be great.
This is actually it. We achieved our goals, and I'm open for questions.
Hi, it's Monica. So did you ever consider solar thermal heating?
Yeah, great question. Actually, I have a whole presentation I gave at a conference on that as well. We definitely did, and one of the biggest benefits of going to hot water is you can heat it with a lot of different things. Gas, you're tied with steam, you're tied to gas, but hot water, it really opens it up to different renewable sources. The most obvious one being solar and solar thermal. The challenge for us was that when you look at the potential of heat recovery with our chilled water system and you compare it to solar thermal, the obvious difference is solar thermal, you can just heat it directly with the sun. In our case, we're going the electrification path. Our campus electricity is actually going to be 100% electrified or 100% renewable in the next year or so. And so you could say, well, we're going to be 100% renewable, and our heat pumps will be running on electricity that's renewable as well. So the path we're going is also 100% renewable, but a little more complex. But the challenge is that they both have a similar profile. So if you look at what solar thermal does, you get all your heat out of the solar thermal in the summer, and you get a lot less in the winter here. Same with heat recovery, right? You get all your heat recovery in the summer when you're doing all your cooling, and you can recover that heat. In the winter, you don't have enough. So trying to marry the two up didn't work well, because when we need more heat with either solar thermal or heat recovery is in the winter, and they both make the most heat in the summer. with solar thermal, the main challenge was there's a big expense to put in all the solar thermal farm, this bunch of panels that are going to cost a lot. And if we're going to size it in a way that's going to actually serve the needs of the winter, then we're going to have too much in the summer. And so unless you have a smaller system where you can do some kind of seasonal storage, that didn't work as well for us, and mostly because we already have a chilled water system. If we didn't have our district cooling system to do heat recovery, solar thermal would have been the best option. So in fact, we have another district system at our primate center on the west of campus, and we are doing solar thermal there because we didn't have as much cooling in the winter, and so there wasn't that heat recovery opportunity. So solar thermal is very much a good option with the right kind of fit.
Yeah, I would like to follow up with you on that later on.
Great.
Thank you.
Yeah, and Ben reminded me that we have a global energy managers workshop that other campuses are doing a lot of cool stuff. We like to get campuses and anyone involved in this type of work together to share both on district energy or other optimization opportunities. We feel like what we're doing, we want to share what we're doing with other campuses, cities, anyone who's involved in this type of work. So we do have this coming up. I don't know if Ali wants to talk about it at all, but it's something that we'll be definitely advertising for. I think it's going to be virtual this year in October, but we'll host it on campus at some point here in the future.
Yeah, and if you're interested, I just sent everyone Josh's email, contact information. And if you're interested in learning more about the Global Energy Managers Workshop, which was probably going to be October 12th to 14th remotely, I will send a quick note to folks. You can just send me an email, make sure you're on our distribution list for that. And we'll also mention it in future seminars as well. But we'd love to have your participation. And we look forward to having it in person again, hopefully next year. But hope you can participate this year remotely. If you have any other questions, we have time for maybe one more, and then we will hope to see you next week or see you remotely next week.
Ben asked one about implications for the opportunity to install more solar capacity on campus. So if we have this heat pump system now doing heat recovery, our electrical usage is going to go up, especially in the winter. And so the opportunity there is with the storage, we're going to be doing heating storage and chill water storage would be to potentially run our heat pumps and run our chillers at times that we can leverage our solar PV system. So if we have a 16 megawatt system on campus, that basically reduces our draw off the grid. So if we can align our electricity demand with our production, that would really impact our draw off the grid and potentially allow us to even upsize our on-campus farm if that made sense. Right now we're limited by not being able to export, but of course if we're using more as a base load, we could have a larger farm without exporting. So there's a lot of questions around that and optimization. We're doing optimization of it now with our chill water system, but when we throw in heat recovery, it's going to get a lot more exciting and complicated.